On a network of thousands of server racks, data streams converge toward a central node, creating a point of congestion as traffic grows. This congestion was a structural reality in Hadoop 1.x. In that architecture, the cluster's resource management and its data processing execution engine, MapReduce, were tied together in a single control plane. A single master daemon, the job tracker, was tasked with monitoring the cluster's health while simultaneously managing every task's execution state. As organizations scaled their hardware and diversified their workloads, this dual responsibility forced the masternode to compute global telemetry and task logic simultaneously, leading to the system-wide failures seen at enterprise scale. These early platforms could not expand their capabilities as long as compute coordination remained trapped inside a single execution pipeline. The path to scaling required decoupling resource allocation from the processing logic. Introduced with Hadoop 2.0, YARN, yet another resource negotiator, functions as a cluster-wide operating system. This separation allows batch workloads, rapid interactive queries, continuous streaming data, and machine learning engines to plug into the same cluster side by side. YARN provides the governed environment that arbitrates raw compute capacity among these competing engines, rather than processing the data itself. The architecture begins at the bare metal level, looking at a massive pool of commodity servers. On every worker node, a local agent, the NodeManager, monitors CPU, memory, and disk usage. These agents report their local health upward through a unified telemetry stream to the ResourceManager, which maintains a global ledger of capacity and arbitrates resource requests. While this loop centralizes the hardware state, the system still needs a way to orchestrate applications without pushing the logic back to the central master. YARN manages compute through the container, a fundamental abstraction where resources are partitioned into strict, measurable bounds. These geometric bounds enforce predictable isolation. If a specific task attempts to consume excessive memory, the container prevents that process from destabilizing the rest of the worker node. To manage work within these containers, YARN utilizes a decentralized controller, the application master. Every job submitted to the cluster spawns its own application master. This controller manages the task lifecycle and communicates directly with its assigned worker containers. Because this controller is application-scoped, frameworks like Spark or Hive can bring their own specialized execution and retry semantics to the shared cluster. Pushing orchestration logic down to the application level eliminates the central master bottleneck that constrained earlier distributed systems. We can see this distributed negotiation by tracing the steps of a workload submission. The client submission first registers with the resource manager, which allocates a single container. The node manager launches the application master, which then negotiates back with the resource manager for the specific resources needed to complete the job. The application master requests container sizes and data locality preferences. The resource manager grants these requests, spawning containers across nodes where data resides. Once finished, the application master deregisters. Containers dissolve, and the global ledger updates instantly to reflect the newly freed capacity. This explicit handshake ensures resource management remains consistent, even when different engines share the same hardware. When many teams share a single cluster, the system must decide which workloads take priority for the available capacity. In a first-in, first-out, or FIFO queue, a single massive batch job can block the entire pipeline, forcing small, time-sensitive queries to wait until the large job finishes. The capacity scheduler divides the cluster into hierarchical queues. A massive batch job runs in one branch, while interactive queries flow through another. If one queue is idle, active queues can temporarily borrow its capacity, increasing throughput without violating minimum guarantees. In contrast, the FAIR scheduler dynamically redistributes resources so that every incoming job quickly receives an equal share of compute. This scheduler can use preemption to reclaim containers from overserved workloads, ensuring that waiting applications meet their minimum resource targets. These algorithms are what allow organizations to enforce multi-tenant boundaries without wasting idle hardware. In production, these isolated containers and scheduling policies allow radically different workloads to coexist. At Royal Research, architects use YARN to manage complex environments in highly regulated sectors like finance and healthcare. These deployments run secure ETL pipelines alongside machine learning cohorts on the exact same cluster nodes. Because the allocations are containerized, A memory-heavy machine learning stage can be tuned differently than a CPU-heavy transformation, all without redesigning the underlying hardware. Without YARN's abstraction, organizations would be forced to build and maintain separate hardware clusters for every processing framework they use. Distributed infrastructure matured only when resource management was treated independently from data processing. The combination of the ResourceManager, NodeManager, container, and application master provides the policy and distributed control necessary for large-scale operations. In modern architecture, scheduling policy is the primary mechanism used for scaling. Decoupling resource allocation from execution logic is what turns a collection of servers into a scalable cluster operating system.